Good morning, Year 10. Today we are starting our topic on measurements and surds. We're going to start with irrational numbers, including surds today. Real numbers are made up of many special types of numbers. These can be real numbers that are separated into two categories here. So our real numbers can be separated into our rational numbers and our irrational numbers. The rational numbers are things like integers, which is your positive numbers, your negative numbers, and zeros. Fraction, of any fraction is a rational number. Any finite terminating decimal, so 0.5 for example, that can also be considered a rational number. And recurring decimals, because they can be written as fractions, they are rational numbers. So that's a lot of things. The things that are irrational are the non-recurring decimals and surds. And there are some very special numbers like pi that we've learnt, and there's another one that you learn in senior school if you do advanced maths, which is e. So they are our irrational numbers. So we're focusing on surds in this lesson today, which is a type of an irrational number. A surd can be written with a normal square root sign. Most of the time they're the ones that we use, but there are also things like cubed roots and fourth roots that can happen as well. Example of irrational numbers are square root of 5, the cube root of 7. Okay, so they're things that if you put in the square root of 5, for example, you get a decimal number that has no pattern to the decimals that are in there. However, something like square root of 4 is exactly equal to 2. So even though it does have that square root sign over it, the answer is rational, which means that it is not really a surd. So to simplify our surds, we need to know what our perfect square numbers are. So 1 times 1 is 1, but that doesn't really help us simplify anything. 2 times 2 is 4 is the first useful number when it comes to simplifying surds. Then 3 times 3 is 9, and 4 times 4 is 16. And so these are all the square numbers. So keep those numbers handy. We're going to need those in a minute. Let's move into our examples. Example number 1. State whether each of the following numbers is a surd or not. Okay, so we're just going to check these with our calculator. If we type in square root of 5 and we get a yucky decimal answer, that means that that one is a surd. Whereas if we type in square root of 0.64, we actually get it's still a decimal, but it's a nice definite decimal. And if I press my SD button, I could even turn it into a fraction if I wanted to. So that one is not a surd. Okay, the cubed root of 27. So we press Shift surd button to bring up the cubed root. 27 equals, and that's exactly equal to 3. So that is not a surd. And the fifth root, so I need to press Shift and the X with the box on it, so I can put a fifth root in there and 25 in there. And so that makes a yucky decimal number, which won't change into a fraction. So that one is a surd. Okay, on to question 2 and simplifying our surds. So I'm going to write our perfect square numbers down the side here. So we have 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. We keep going, but you don't often get numbers above 100 that need simplifying. So if I want to simplify the square root of 20, I want to find two numbers at times to give 20, but one of the numbers has to be a perfect square number. So doing 2 times 10, for example, is not helpful because neither of those numbers are perfect square numbers. However, 4 times 5 is 20, and 4 is one of my numbers right here. So I split the surd into the timetable that I just worked out. So square root of 4 times square root of 5. Then you can square root the perfect square. The square root of 4 is 2, and you put it next to the root 5, and that is a simplified surd. Let's try it again. Square root of 8. So 8's not a very big number. The only perfect square number that is less than 8 is the 4. So luckily 4 works because 4 times 2 makes 8. So I split the surd to be square root of 4 times square root of 2. Again, the square root of 4 is 2, so it will be 2 root 2. Moving on to question C on the next page. We want to do the number 80. So looking at the square numbers up here, 80. You might want to use your calculator if you're not sure what things times to give 80. So you might go 80. Yes, it does divide by 4, but I think we can go bigger than that. If we tried 9, it wouldn't work. But if we tried 16, it goes 5 times. So we're going to split 80 to be square root of 16 times square root of 5. The square root of 16 is 4, so the answer is 4 root 5. Part D. Don't worry about the 6 out the front. We want to simplify the square root of 18. So looking at our numbers, we can use the number 9 because 9 times 2 makes 18. So we put square root of 9 times square root of 2. The square root of 9 is equal to 3, but because I already have another number there, I want to times the 6 with the 3, and then the root 2 will be sitting on the end. 6 times 3 is 18. So the answer is 18 root 2. E first, sorry, E. 5 root 40 all over 6. We want to simplify the square root of 40. So the perfect square number that works will be 4 times 10. So we're going to split, leaving the 5 out the front. We have root 4 times root 10 all over 6. The perfect square is the 4. So the square root of 4 is 2. And you times the 2 with the 5 to make 10 root 10 over 6. Now the 10 and the 6, the normal numbers at the front here, neither of them are surds. I can simplify those down by dividing by 2. So I would get a 5 on the top and a 3 on the bottom. My final answer, therefore, is 5 root 10 over 3. Question F. When you are simplifying a fraction underneath the surd, there is 2 ways that you could do this question. So I'm going to do it both ways just to show you. First of all, you could simplify down the fraction underneath. So if I typed in 75 over 9, it simplifies down to 25 over 3. So it's the same as square root of 25 over 3. Then you could split the surd to be square root of 25 on the top over square root of 3 on the bottom. And fortunately for us, the square root of 25 is 5, and then we would just have a square root of 3 on the bottom. Okay, let me show you option number 2. Or the other way to do it would be to split the fraction into 2 surds straight away, meaning that we would have square root of 75 over square root of 9. Square root of 75 we can simplify down. 75 is 25 times 3, so we'll split that to be root 25 times root 3. Square root of 9, 9 is a perfect square number, so square root of 9 is exactly equal to 3. On the top, square root of 25 is 5 root 3 over 3. Now they are 2 different answers, and both of them are acceptable working out, but this second way that I have done here is the better option. The reason it is better is because of the 3 on the bottom of that fraction, because it is what we call rational. So we're going to be learning about rationalising the denominator in a coming up lesson, but we prefer to have our answers with whole numbers on the bottom, not surds. So that's what makes that second one the better option. Moving on to question 3. Express these surds as a square root of a positive integer. What that means is I want to reverse the simplification process so that I put whatever's at the front here back underneath the surd. I want it all written as one square root sign with nothing else out the front. So to do that, I'm kind of doing the opposite thing. The whole number 5, I want to turn it into a surd. So I could say that 5 is the same as square root of 25. That's the surd that I know. That would be the same thing. So square root of 25 times the square root of 3, and then you multiply the numbers underneath those surds. So you go 25 times 3 is square root of 75. Let's practice that again. For B, the 11 out the front, we want to turn that into a surd. So 11 times 11 is 121. So square root of 121 is 11. We times that by the root 2. Then we times the numbers underneath the square root signs. 121 times 2 is 242. Okay, question 4, we wanted to start doing some application types of questions. Question 4 says, determine the exact side length in simplest form of a square, so here's my square, that has an area of 200 millimeters squared. And I want to know the side length. So the side length for a square, we usually call that L, because the area of a square formula is A equals L squared. If I sub the area into that little equation, I would have 200 equals L squared. Then to solve and find out what L is, I would need to square root the 200. Now, often when we square root things, we have plus or minuses, but lengths cannot be negative, so we only have the positive version of this square root. So I have found the value of L, but the question did say in simplest form. Exact, so I want to insert, but simplest form. So I want to simplify the square root of 200. Now, thinking of my perfect square numbers, 200 is 100 times 2. And 100, the square root of 100 is 10. So 10 root 2 is the length, which would be in millimeters of that square. Over the page to question 5. Determine the exact radius, exact meaning we're probably going to have to leave things in surd form again, radius and diameter of a circle in simplest form that has an area of 54 pi meters squared. So the area of a circle has the formula A equals pi r squared. The area that I've been given is 54 pi, which will be equal to pi r squared. And I'm going to solve this equation to find out what r is. Now, we don't really like having all these pi's floating around in our equation, and the good news is that we could divide both sides by pi, and the pi symbols would cancel out. That would just leave 54 equals r squared. Then, to get the r by itself, we would square root the 54. Again, we only want the positive version because this is the radius of a circle. To simplify that surd, we're thinking what perfect square number goes into 54? The answer is 9. It is 9 times 6 that makes 54. Square root of 9 is 3, so my simplified radius is 3 root 6 meters. But just to be thorough, we have to go back to our question. The question said determine the exact radius and diameter. So the radius is 3 root 6 meters, and the diameter would be twice as big as that. So twice as big as 6 root 6, 3 root 6 is 6 root 6 meters. Okay, that would be a challenging type of question, that one. And also part question 6 here. Use Pythagoras' theorem to find the length of the unknown side in the triangle below in exact form. So we're trying to find the hypotenuse over here in exact form. There are a few different versions of Pythagoras' theorem that you're probably familiar with, but the formula that I'm going to use is that the hypotenuse is equal to the square root of a squared plus b squared, which is the two shorter sides squared and added together. If I substitute in, so I'm going to say a is the root 7 and b is going to be the 2, I would get square root of root 7 squared plus 2 squared. Root 7 squared, a squared and a square root, they undo each other, so that's just equal to 7. And then 2 squared is 4, so 7 plus 4 makes 11, so the answer is square root of 11. You could do the underneath part of that on the calculator, so you could go square root of 7, close bracket, whoop, I put that in the wrong spot, close bracket, and then squared, and then plus 2 squared, so that is equal to the 11, and I just put the square root sign over the top of that to keep it in surd form. That is in meters. Okay, so that's the end of our theory section. You now need to do exercise 4A.